Take a series of still, sequential images. Let's look at them one by one. Faster. Now let's remove the gaps. Go faster still. Wait for it. Bam! Motion. Why is that? Intellectually, we know we're just looking at a series of still images, but when we see them change fast enough, they produce the optical illusion of appearing as a single, persistent image that's gradually changing form and position. This effect is the basis for all motion picture technology, from our LED screens of today to their 20th century cathode ray forebears, from cinematic film projection to the novelty toy. Even, it's been suggested, all the way back to the Stone Age when humans began painting on cave walls. This phenomenon of perceiving apparent motion in successive images is due to a characteristic of human perception historically referred to as persistence of vision. The term is attributed to the English-Swiss physicist Peter Marc Roget, who in the early 19th century used it to describe a particular defect of the eye that resulted in a moving object appearing to be still when it reached a certain speed. Not long after, the term was applied to describe the opposite, the apparent motion of still images, by Belgian physicist Joseph Plateau, inventor of the phenakistoscope. He defined persistence of vision as the result of successive after-images which were retained and then combined in the retina, making us believe that what we're seeing is a single object in motion. This explanation was widely accepted in the decades to follow and up through the turn of the 20th century, when some began to question what was physiologically going on. In 1912, German psychologist Max Wertheimer outlined the basic primary stages of apparent motion using simple optical illusions. These experiments led him to conclude the phenomena was due to processes which lie behind the retina. In 1915, Hugo Münsterberg, a German-American pioneer in applied psychology, also suggested that the apparent motion of successive images is not due to their being retained in the eye, but is superadded by the action of the mind. In the century to follow, experiments by physiologists have pretty much confirmed their conclusions. As it relates to the illusion of motion pictures, persistence of vision has less to do with vision itself than how it's interpreted in the brain. Research has shown that different aspects of what the eye sees, like form, color, depth, and motion, are transmitted to different areas of the visual cortex via different pathways from the retina. It's the continuous interaction of various computations in the visual cortex that stitch those different aspects together and culminate in the perception. Our brains are constantly working, synchronizing what we see, hear, smell, and touch into meaningful experience in the moment-to-moment flow of the present. So in order to create the illusion of motion in successive images, we need to get the timing of our intervals close to the speed at which our brains process the present. So how fast is the present happening according to our brains? Well, we can get an idea by measuring how fast the images need to be changing for the illusion to work. Let's see if we can figure it out by repeating our experiment. Here's the sequence, presented at a rate of 1 frame per 2 seconds, with 1 second of black in between. At this rate of change, with the blank space separating the images, there's no real motion perceptible. As we lessen the duration of blank space, the slight change in position becomes more apparent, and we start to get an inkling of a sense of motion between the disparate frames. 1 frame per second. 2 frames per second. 4 frames per second. Now we're starting to get a feeling of motion, but it's really not very smooth. We're still aware of the fact that we're looking at separate images. Let's speed up. 8 frames per second. 12 frames per second. Looks like we're about there. At 24 frames per second, the motion looks even smoother. This is standard full speed. So the point at which we lose awareness of the intervals and begin to see apparent motion seems to kick in at around 8 to 12 frames per second. This is in the neighborhood of what science has determined to be the general threshold of our awareness of seeing separate images. Generally speaking, we begin to lose that awareness at intervals of around 100 milliseconds per image, which is equal to a frame rate of around 10 frames per second. As the frame rate increases, we lose awareness of the intervals completely and are all the more convinced of the reality of the illusion.